So chemical reactions occur in several steps. And when we look at the chemical equation, we just see what's there at the beginning and what's there at the end. And to avoid our previous problem, we'll pay attention to the coefficient here. So H2 reacts with two ICLs to form two HCl and I2. And when we look at this overall reaction, we can't tell exactly how that's happening. We might say, well, it kind of looks like this H2 has to run into two ICLs at the same time, and all three of these things have to hit and make the products, right? That doesn't sound very likely. And when we look at the reaction mechanism, we see the individual steps by which the reaction occurs. And that's not how this reaction occurs. So in the reaction mechanism, we have elementary steps, and each of those steps tells us exactly what two things are colliding to react. So for this one, in the first step, hydrogen collides with ICl, and it'll make an HI and an HCl. So this is one of the products. That's fine. It's stable. It's just going to go off and do whatever it does. This HI is going to collide with another ICl, and this combination is going to make HCl and I2. And so if we take those individual steps and add them together, we see that this HI that was formed in the first step gets used up in the second step. And so we end up with H2 plus 2 ICl gas plus 2 HCl gas plus I2. Yeah, so the HI is a reaction intermediate. It is formed in the first step but destroyed in the second step. And so it's not one of the reactants, and it's not one of the products either. It is present during the reaction, but it gets made and used up. So that's a reaction intermediate, formed in one step, used in another. Now hopefully it made a little more sense now that I explained it correctly. Questions? Yes?
When we were doing the Hess's law stuff in Chem 1A, were we dealing with the same kind of reaction mechanism, or is that a different concept?
That's a slightly different concept, yeah. Anybody else? So the reaction mechanism is a very detailed description of how the reaction happens on the molecular level. Shows what things are colliding. So it can be very useful. Chemical kinetics can help us determine the mechanism of a reaction. Mechanisms can be very challenging to figure out because we can't get out a microscope and actually see what's happening. And so it's like working with a black box, and we have to figure out, well, if we do this, this happens. If we do that, that happens. It does make it more interesting, but more difficult. So we can use chemical kinetics to help us figure out the mechanism of a reaction. If we measure the kinetics of the overall reaction, we can often work backwards to write a mechanism that's consistent with the kinetics. And that may end up being the correct mechanism, or maybe not. So the elementary steps are characterized by how many particles are involved in the step. It's called the molecularity. How many molecules are involved? Now, by molecules here, we're really meaning particles. So in a unimolecular step, you just have one thing that's reacting. In a bimolecular step, you have two things that are colliding. They could be two atoms or molecules of the same species. They could be two molecules or atoms of different species. Termolecular steps have three particles colliding simultaneously. Those do happen, but they're very rare. Most reaction steps are either unimolecular or bimolecular. Rate laws for the elementary steps can be deduced from their equations. So it's important to understand that what we're looking at here is for elementary steps. This is not for the overall chemical reaction. We can't look at an overall chemical reaction and figure out what the rate law is. We have to do experiments and figure it out. When we're looking at an elementary step where we can see the two things that are actually colliding, then the rate law can be deduced from the elementary step reaction. So here, if we have A forming products, this has a molecularity of 1, and the rate law is going to equal the rate constant times the concentration of A. Here we have A plus A making products. The molecularity is 2. We need 2 molecules of A. So here the rate is going to be second order Ka squared. Yes?
So when you say A plus A, you mean that the reaction must happen twice in order to make the final product?
No, not quite. What I mean is by A plus A is that 2 molecules of A have to run into each other.
Okay.
This first one that's unimolecular, A doesn't run into anything. It just, for whatever reason, decides to split up into products. It just breaks spontaneously. Here we have 2 of A colliding with each other. Here we have A and B colliding. So one piece of A and one piece of B run into each other and make products. So this is also bimolecular, and its rate law is second order, but now it's got the concentration of A and the concentration of B. It's first order in each of them, but second order overall.
But like with respect to?
Yes. First order with respect to each,
So
because the exponent is 1.
All combination reactions are second order.
Well, we can't say that all combination reactions are second order. We can say that all combination elementary steps are second order. But this elementary step, either this one or this one, doesn't necessarily match up with the reaction itself. Yeah.
Probably isn't too important, but for the first molecularity step,
Mm-hmm.
When you said they're probably just breaking apart in making
Mhm.
products, are they doing that because of collisions, or they're just like decomposing?
It's not doing it because of collisions,
Okay.
because this elementary step indicates that all you need is a molecule of A.
Okay.
It doesn't have to have anything else to bump into. So that's one where the collision is not required
Okay.
for this step. And then here we have examples of termolecular steps. These are very rare, but they do happen. We might need 3 of A to collide, 2 of A and 1 of B, or maybe 3 different things. And so these rate laws over here would all be third order overall, but it's going to depend on how many of each of these, the order with respect to each reactant. Any questions? What's dangerous about this is that we look at this and we like this so much. It's like, well, A plus A, that's 2A, and so here Ka squared, 2, that's the coefficient, right? Yes, for elementary steps only. We can't do this with just every reaction we see. So we just have to be very careful. So in that series of elementary steps, one of them is usually slower than the others. And that's the rate determining step. And it limits the overall rate because the overall reaction cannot happen faster than the slowest step. So it's a little bit like a traffic jam. So here you have some road work happening, and this 3-lane highway is going down to 1 lane. This is like the rate limiting step, that slowest elementary step. Cars can come up fast to this point, and they can go fast after that point, but here everything gets bottlenecked, right? And it slows down. So you can't make this trip faster than you can get through this one section. Any questions? So here's a reaction. NO2 plus CO makes NO plus CO2. And the experimentally determined rate law is the rate is equal to a constant times NO2 squared. Okay, we cannot get this directly from that equation. This was determined experimentally. And so the question is, could this be a single-step reaction? Could this be the elementary step? If this is an elementary step, what would the rate law be? Yeah, it would be second order, but it would depend on the carbon monoxide concentration. If this is an elementary step, then the rate law would be this, rate equals. But we determined experimentally that the rate law was this. So this cannot be a single-step reaction where one of these collides with one of those and makes the products. So there must be something else going on. Any question?
How do you determine if it's like
Well, I can't, if this matched with the experimentally determined rate law.
Oh, so since it gives you the rate law, you know that it's not that.
Right. So if the experimentally determined rate law was this, which matches with this being an elementary step, then I could say, yeah, it's a single step reaction. But because this does not match with that, we can say it must occur in at least two steps.
What if we're not given experimentally, or will we always?
Well, there's no way for you to know what the experimentally determined step, what the experimental actual rate law is unless we tell you. Except for if we're doing an experiment where that's what you're determining.
So anytime that a rate law is rate K times the concentration of each reactant, we know it's a single step?
Yeah, if it would be each reactant raised to a power that's equal to their coefficient.
Okay.
Yeah. And that's unusual. Doesn't usually happen. So here's a possible mechanism that NO2 and NO2 run into each other, and basically one of these gives an oxygen to the other, and we end up with NO3 and an NO, and that this is the slow reaction. And then after that, the NO3 runs into the CO, and that gives us NO2 and CO2.
How can we determine which one is slow and which one is fast?
That's a good question. How would we determine? If we were given these two steps and told that is the mechanism, we could choose this one as the slow step because that matches with the experimentally determined rate law. The rate law for the overall reaction will correspond to the rate law for the slowest step. If we add these two things together, we see that NO3 is a reaction intermediate. And then we also end up remaking one of these NO2s so we can cancel one of those out as well. And we get NO2 plus CO makes CO2 plus NO. Or, backwards. But the overall reaction is the same as adding these two mechanism steps. We can predict the rate law for each of these individual steps. Here, the rate would equal a constant times NO2 squared. And here, the rate would equal a constant times NO3 times CO. Yeah.
The book says that, a valid mechanism is not a proven mechanism, but experimental evidence for proposed intermediate may exist. What kind of evidence would that be?
That's an excellent question, because just because we came up with this on paper doesn't mean that it's actually true. And so then how do we evaluate if it is actually true? There's a lot of different ways that you could go about doing that. If you had a way to identify whether NO3 was present, and you found that NO3 was present, even though it's not a reactant and it's not a product, that would suggest that it is at least one of the reaction intermediates, and it would support this hypothesis. Sometimes you can do things that will alter the rate of one of these and not the other. There's a lot of fiddling around you can do. And it's like a big puzzle. Yeah. Did you have a question? Okay. Yeah. So, identifying reaction mechanisms, there's this whole separate area of chemistry, right? And some people are really into that. And it's really cool.
So is this also kind of like the rate law that like it can only be like confirmed, correct? Through like experimentally?
Well, the only way to confirm that this is the rate law is to do experiments where you change the NO2 concentration and you measure the rate.
Right.
Yeah.
But then like, I'm talking about the intermediates, so like that can only be proven true through the experiment, correct?
Yeah, you'd have to do an experiment to see if that actually was being formed. Because there's lots of things we can dream up on paper that don't actually happen. And then there's some things that actually happen that we never would have thought of, because nature is just that strange.
Now, are there patterns when determining elementary steps? Or not necessarily?
Well, why don't we finish the lecture and then answer that question. So we can draw an energy diagram for the individual steps. And so here we have a two-step mechanism. Starting out with the reactants, there's an activation energy, we get to a transition state, and then that's our first step, is up here. And then there's a second step, and the second step has a smaller activation energy, and then we end up with the products down here. This first one with a higher activation energy, because the activation energy is higher, it has a smaller rate constant. So this is most likely going to be the slowest step. Here with the smaller activation energy, it's going to be faster. And so what's going to happen with this overall reaction rate is that it's going to depend on this first step. Because once we get up here, it's literally all downhill from there. You just have to get up and over this hump, because then if you think about balls rolling down hills or something, if you start here and you roll the ball down the hill, it's going to have enough momentum to go up and over this little hump and get down just fine. But it's this highest part that we have to get over. So, conditions for a valid mechanism. The elementary steps in the mechanism have to sum up to the overall reaction, and the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. You can't prove that a mechanism is true, you can only validate it. Well, we couldn't prove it wrong. Looks like it's correct, but there could be other mechanisms that also meet those conditions. The steps add up to the overall reaction, and the rate law is the same as experimentally observed. So then you need other data to strengthen that. If we have a mechanism where the first step is fast, then the rate law that's predicted by the rate limiting step can have reaction intermediates in it. Because the first step goes fast, it makes an intermediate, and then that intermediate is involved in the slow step. So then if you look at a rate law predicted by the elementary step, you end up with a rate law that has intermediates in it instead of just reactants. So that doesn't work out very well. The rate law cannot have intermediates in it. because when we determine the rate law, we're not looking at intermediates, we're only looking at reactants. So how do we deal with this? When the first step is fast, it may be fast enough to establish an equilibrium so that the reactants are forming products, the products are reforming reactants, and it's going both ways, but in equal rates. As an example, 2 hydrogens reacting with 2 nitrogen monoxide molecules to make 2 water molecules in N2. Yeah.
For the last slide, how do you know, like, what, if you go back, because it says, when it's fast enough, so that's kind of,
We're going to assume it's fast enough.
okay.
It gets really icky if it isn't. Yeah. This is the beauty of general chemistry. We can just gloss over some of those unfortunate details that make things complicated. Well, it's like, yeah, well, we'll talk about that later. So here's the observed rate law. It's first order for hydrogen, second order for nitrogen monoxide. And you notice this does not match what you would predict from that as an elementary step. They did experiments where they measured the rate when they changed concentrations, and they came up with this. So then you can propose a mechanism, and this is the proposed mechanism, that 2 of these NOs are going to get together and make N2O2. This is fast. Then we have this slower step where H2 reacts with one of those, with that, to make H2O and N2O, and then the N2O reacts with hydrogen to make N2 and H2O. Okay, and so what this is saying is show that condition 1 is met, that the elementary steps add to the overall reaction. So in order for this to be a valid mechanism, when we add these reactions together, they have to give us what we've got up here. So to demonstrate that, we're just going to add these together. So make sure that you keep your arrows kind of lined up. I'm just going to, so we got to make sure that we don't cross things off on the same side. So there's an N2O2 on this side, and there's an N2O2 on that side. So this gets made and then it gets destroyed. And what else do we have here?
Dinitrogen monoxide.
Yeah, we've got this dinitrogen monoxide. So N2O gets made and it gets used up. And so now this is looking pretty good because I'm only seeing the things that are actually in the original. So I've got 2 hydrogens left after I cancel out everything that got made and destroyed. And I have 2 NOs. And here's my arrow. And then over on the other side, I have 2 water molecules and 1 nitrogen. So the first condition, that the elementary steps add up to give the overall reaction, that is true. Any questions? Condition 2 is that the rate law predicted by the mechanism is consistent with the observed rate law. So predicted by the mechanism, the first step was fast, the second step was slow. It's the slow step that limits the rate of the reaction. So if we were going to write a reaction rate law based on this slow step, we would have rate equals constant times H2 and N2O2. Right? Yes.
So what's the difference between an observed rate law? That's just like what we do. Like it was like on the previous slide it said the observed rate law.
Mm-hmm.
And then it had a 2 as an exponent.
Yeah, so the observed rate law is H2NO squared. So we actually have the reactants, H2 and NO, those are the only things present here. Nope, I lost it. It's okay. When we predict from this second step, we end up with something that's different. I've got H2, but now instead of, you don't like my H? I'm just going to pretend it's the computer doing that, even though it clearly was not. So from this step, we predict hydrogen concentration to the first power, because its coefficient is 1. It's Monday. It was a long weekend. And this one, because the coefficient is 1. Yes.
So with the coefficients on the last slide,
Mm-hmm.
how is each 2 not 2, or doesn't have second order on it on the previous slide?
Right. So from that overall reaction, if we were going to, if that was an elementary step, it would be H2 squared in NO squared.
Okay.
But it's not.
Wait, which one is it?
If I do it on here, I'm going to lose my other thing. And we see what happens when I try to do that again.
Yeah.
So this guy up here,
Yeah.
so it's 2H2, so this would be H2 squared,
Yeah.
and this would be NO squared. If that example 1 up there was an elementary step, if that represented the actual collisions that happen. But it's not. We do an experiment, we test it, and we find out that it's second order for NO and first order for H2. And so there must be something else happening in the reaction.
We see that though, because we add it all up. I mean, of course, it goes back to what the initial equation is. But if we have two dihydrogen atoms or molecules left, that would just. How do we know it's just one of those used for the rate, or it's just the first order?
Because you did an experiment.
Okay.
Yeah, there's no other way. There's no other way. And that's why I said we have to be careful, because it seems so easy. We just, it's just the coefficient is the exponent. Yeah, only for elementary steps.
Okay.
So the tendency then is we want to do it for everything, because it's so much easier than comparing, well, when this changed, the rate did this, and all that other stuff that we did first. Like, well, why do we have to do that? Well, because this, you just can't do that. Okay? So what we need to do here is somehow get the N2O2 out of there. And I can't remember what's coming up on the next slide. Yeah, it's just all here. Okay. So we can express N2O2 in terms of the reactants of the overall reaction. And so what we're going to do is we're going to look at this first reaction here, and we can predict a rate law for the forward reaction. We'll call that rate forward, and that would equal the rate constant forward times the NO concentration squared. You okay with that? So this going forward, NO squared times the constant, that's the forward rate. If that's at equilibrium, the reverse rate is the same. We can write an expression for the reverse rate law. So that's taking N2O2 and making 2NO. So that would be another rate constant times the concentration of N2O2. So rate law for forward reaction, rate law for the reverse reaction. Are you with me? This means yes. This means no. Could you say that again? I don't see any shaking heads. A lot of still heads. So if this is equilibrium, then the forward rate is equal to the reverse rate. Okay? Which means that this thing is equal to that thing. Okay? And some of you are like, oh, I see where this is going. So we can say that that forward rate constant times NO squared is equal to the reverse rate constant times N2O2. Now, see, in my predicted rate law here from the elementary step, I have N2O2, which is not one of my reactants. I need to get rid of this somehow. So I can do this business, and then I can rearrange this and solve for N2O2. I'm just going to divide both sides by Kr. Oops. The Krs cancel out. Yes?
Why would we set them equal to each other?
That's an excellent question. Why would we set them equal to each other? Because this is an equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. Yes?
Now, will that be told to us, or will we have to figure that out?
Those arrows tell us, right?
The arrows tell you.
Right.
Yeah. And the fast tells us. If the first one's fast, in this class, we're always going to assume that it sets up an equilibrium.
Okay.
Because we're not going to learn how to do anything else.
Okay.
Yeah. So now I've got N2O2 is equal to Kf over Kr times NO squared. So I can put that into my equation over here. So my rate is equal to my real rate constant and H2, well, some rate constant anyway. And then for N2O2, I'm going to put in Kf over Kr times NO squared. So this thing that was a reaction intermediate, I figured out a way to express it in terms of an actual reactant.
So we're trying to get rid of N2O2 because of the observed rate law, it was NO, right? So that's what you're trying to get.
Yes, and also since this is not a reactant, it's a reaction intermediate, we can't have reaction intermediates in the rate laws because we can't measure them. They get made and destroyed, and we can't control them. So we can only have reactants, actual reactants. We can't have reaction intermediates in our rate laws. So then what we're going to do here is this is a constant, that's a constant, that's a constant. We don't care what they are individually. We can put them all together and they're still going to be a constant, right? So we're just going to say the rate is equal to a constant times H2 times NO squared.
Explain that one more time.
So let's I'm going to put a subscript on this other K. I'm going to call this K1, just so it doesn't look like it's trying to be the same thing as my ultimate K. I'm going to say that K is equal to K1 times K forward divided by K reverse. So I'm taking all of these constants in this rate law and I'm lumping them into one rate constant. Because there's only one rate constant for the overall reaction. And I did all this math hocus pocus here, and I was looking at these rate constants, but in actuality, what they are doesn't matter. They're constant, and so they're just part of the overall rate constant. And so I ended up with a rate law that is the same as the observed rate law.
What's the equation in the very top left?
This one?
Yes.
So this is the rate law predicted by the slow reaction step, the slow mechanism step. These are both elementary steps, and so I can predict rate laws based on those, and this would be H2 and N2O2 times the constant.
So you always look at the slow.
The slow step, yeah. Because if you have fast before, fast after, those don't affect the rate. It's just the slow step that affects the rate. Any other questions? Yeah.
So you would have the slow one and then you would make it, like you manipulate it to be how
Yeah, when we have a fast initial step, our slow step is probably going to have reaction intermediates in it. And so then the rate law isn't going to match up with our experimentally observed rate law. So that's when we have to do this and express that the concentration of the intermediate in terms of the concentration of a reactant. Yeah. Isn't this fun? Yeah.
Can there only be one slow step?
That's a good question. Can there only be one slow step? I think it's safe to say that most of the time there can only be one slowest step, right? Because I suppose in theory you could have two slow steps that happen at exactly the same rate, but then would it really matter?
So it'll be labeled, it'll be clear which one.
Yes. Yeah. They'll be labeled slow and fast, and we're not going to care about how slow or how fast, just one or the other. It's slow or it's fast.
Now this only works if the elementary step above the slow one is at equilibrium, correct?
Yes, this has to be at equilibrium, but with a fast initial step, that's usually a safe assumption,
And that's what we're assuming.
and that's what we're doing. Yeah. Of course, there are exceptions, right? But yeah, when you're just learning things, you can ignore the exceptions. Okay. So this is an example. This could be like a homework problem or could be an exam problem. Ozone naturally decomposes to oxygen by this reaction. 2O3 goes to 3O2. It's kind of some interesting symmetry there. The experimentally determined rate law for this step is rate equals KO3 squared, O2 to the minus 1. That's different. Show that this proposed mechanism is consistent with the experimentally observed rate law shown here, where we got O3, come on. O3 makes O2 and O, that's a fast step, and then we have O3 reacting with O to make O2, and that's a slow step. If this is given to you as a problem, we're generally going to give you a reaction mechanism where the steps add up to be the overall reaction, so we probably don't have to worry about that, but couldn't hurt to check. And just kind of eyeballing this, I can see there's two O3s here, and this O and that O would cancel out, and I'd have three O2s over there, so those do add up. Here we have a fast first step and a slow second step. So I'm going to predict a rate law based on the slow step. So based on the slow step, the rate is equal to a rate constant times the concentration of O3 times the concentration of O. That comes from this step. Everybody with me? Because those are elementary steps, and we can predict rate laws for elementary steps. But this is the actual rate law. Our predicted rate law here has O in it. Oxygen atoms don't show up in the overall equation. And so we've got to express the oxygen atom concentration in terms of something else. So we're going to look at this fast reaction and say, well, that's fast. We're going to assume that's going to be at equilibrium. And so we can say, well, the forward rate is going to equal a rate constant times O3. That's the forward rate here because there's only one reactant, O3. And that's going to be equal to the reverse rate because this is at equilibrium. So that's some other rate constant. And taking this in reverse, we've got O2 and O. Everybody okay with that? Definition of an equilibrium is that the forward reaction is equal in rate to the reverse reaction. So let's try to write this out. Oops. So we come up with this, right? Setting those two equal. And what I want to do is I want to solve this for O, so I get something that I can plug into this and get rid of that term. Yeah.
For the green, why did you use the bottom, the slow one, and for the purple, why did you use the fast?
Because the actual reaction rate is going to be determined by the slow step. So this is a rate law for this reaction, but it's not useful because it's got a reaction intermediate concentration, and we can't measure that. The first step is fast, and so we can assume an equilibrium gets set up, and then this is true. So then I'm going to rearrange this. I'm going to divide this side by Kr and O2. And there we get the oxygen concentration is equal to that.
You know you're going to use that, divide the Kr on 2.
How do I know I'm going to solve for this?
Yeah.
Because this is what I want to get rid of up here. Yeah.
So I'm curious, I might be jumping a little bit too far ahead of what you're trying to do, but if O2 is the product, then how can we include it in the rate law for the reactants?
That's an interesting question. Yeah. Let's not talk about that just yet. We'll finish the problem and then we'll talk about that. Yep.
How do you know to divide by O3 instead of O?
Well, I want to solve the equation for O
How do you know?
because O is in my rate law here and it's not in my experimentally observed rate law. It's not a reactant. It's not a product either. So the only things that can show up in a rate law are actually in the overall reaction. There can't be any reaction intermediates.
And you're solving for that because it's not.
Yeah, because I need to get this out. So what I'm going to do up there is I'm going to replace the O with what I figured out it was down here. K forward over K reverse times O3 over O2. And then I'm going to take this constant and those two constants and combine them all into a constant. And my overall rate then, the rate is equal to a constant, just combining all those things. And then I've got O3 squared, and it looks like it's divided by O2. And that is the same as what is written on the original problem with O2 to the minus 1. Because when you have a negative exponent, that's the same as it being in the denominator. Any questions? Yes?
So all you're doing is you're taking the equilibrium notation and using it as like a literal mathematical equals sign and just
Yes.
subbing back in.
Yeah.
Okay.
So we can predict a rate law from the slow step, but it usually, when we have a first fast step, it's going to have intermediates in it and it's not going to work. If the first step is slow, it's all easy. It's great. Yes?
And you're getting the O3 squared, but you're adding the integer O3 that you're substituting in, right?
Right, so I've got this O3 that was here to start with, and then I've got another O3 in this term I substituted in, and O3 times O3 is O3 squared. I can pretty much guarantee there's going to be a problem like this in the exam, so, yeah. When you see the process, it's like, I can't see the forest for the trees, right? Because I keep running into the trees and I can't get a look at the big forest. You have to back up and see the whole forest. And then it's not that hard. But you have to see the overall picture or it's just a mess and you're lost in the woods, literally.
Well, I think then like O2 is minus 1 at the very end.
So O2 is minus 1 here because it was in the denominator here. Yeah. Okay, so now I can try to explain how you could have a product in your reaction rate law. Well, this rate law says that the reaction rate is inversely proportional to the oxygen concentration. So the higher the oxygen concentration, the slower the rate. The lower the oxygen concentration, the faster the rate. And so it appears that this product inhibits the reaction in some way. It slows it down.
That'll make sense.
Yeah.
Can you say that one more time?
Because this is negative and it's a product, when I have more oxygen here, it slows the reaction down. Yeah. We don't want to think too hard about it. It's just, we're stay on the surface of that one. Okay. Any other questions?
Are you
Mhm.
just saying that, or do you need to really know that?
You don't need to know that. That was an extra question that he asked, and I want to satisfy his curiosity, because that sort of curiosity is awesome. But no, I'm not going to test you on that.
Okay.
If it's not in the book doesn't say anything about that as far as I know. Did somebody else have a question back there?
What happens to the K final over
The KF over KR. We don't care what these are. This is some number that's a constant. This is some number that's a constant. That's some number that's a constant. We have three constants. We're just going to put them together and call them K. Because individually, they really don't have any significance anyway, and we can't figure out what they are.
So, in the end, we get the experimentally determined rate loss. Is that all we're doing? Is just
That's all we're
finding
doing.
it?
Mm-hmm.
We're just
We are demonstrating that this mechanism is consistent, right? That this is a possible mechanism. This doesn't prove that it's correct, but it fits the requirements. When we add these two steps together, we get the overall reaction. And when we predict the rate law from these steps, we get the same rate law that we get from experiment. So this is good that we're probably on the right track. But there could be another reaction mechanism that also works and actually is the correct one. We don't know. And at this point, we don't really care because we're not actually doing that experiment. Okay? Any other questions? Predict the overall reaction and rate law that results from the following two-step mechanism. So this is a little different. Here we're given the mechanism and asked what the equation is and what the rate law is. Well, what's true about a correct mechanism? There were two things. The slow step determines the rate. So for this slow step, what would we predict that the rate law is? Constant times a squared. And since the first step is slow, when we write this expression from the elementary step, we don't end up using a reaction intermediate, and so we don't have to do all that swapping around. But what's the overall reaction here?
2A plus B turns into A.
Yeah, we're going to add the two equations together. A2 is a reaction intermediate that gets formed in the first step and destroyed in the second step. So this is the overall reaction. And this is the rate law predicted. Does that seem too easy compared to the last one? First step is slow, things are so much easier. If the first step is fast and the second step is slow, then you've got all kinds of crazy. Oh, good, I got it right.